Hi everybody. A very good morning to everyone. Good morning, Harita.
Good morning, sir.
Okay, so why is there so less strength today? Any exams are going on?
No, sir.
But still, only 3 of you are there. So I have to be made host, and then we can start. So your school syllabus is completed? Have they completed the syllabus in your school? Only 2 chapters are there. That was 2 very small chapters, right?
Sir, in school we have completed the portions, sir.
Okay. So we will also be completing either by this week. I think we can try, but next week it will be over for you. Okay, I'm the host. Let me share my screen. Okay, so we started with this periodic classification. Hope you remember, right? So we studied what is the need for classification first, right? So we know that the matter, any matter is something which has mass and volume, right? That can be classified into pure substances and mixtures. Under pure substances, we have elements or compounds, right? What do you mean by pure substances? It is going to be made up of single type of entity, single entities, right? So based on what is the single entity, we can have either atoms or molecules, right? If it is atoms, it is going to be called as elements. If it is molecules, it is going to be called as compounds, right? And in case of mixtures, we have homogeneous heterogeneous that we are worrying about for now, right? And in case of right, so if I talk about elements, right, there is a need to classify them, right? Why is the need to classify them? To study them to study them better. This is not once you are able to group these elements into say groups, right? So the elements are going to come under the same group are going to have similar properties, either physical properties or chemical properties. That doesn't matter for now, right? But if you're able to group these elements together, right, under different groups, you will be able to study them together, right? And second thing is, if at all new element is found out, right, and if you can predict which group it is going to belong to without even discovering that particular element, we'll be able to predict, okay, it is going to react like this only, it is not going to react like this. All those things will be able to predict, right? Okay. Now, the first person to even understand the classification of elements was Dalton, right? He just classified elements into solids, liquids, and gases, right? But again, solids, liquids, and gases, that's a good way of classifying. But chemical properties, right? They were not able to predict with the help of that, right? Because different solids, for example, sodium is a solid, magnesium is a solid, but they have different properties, right? Say nitrogen is a gas, oxygen is a gas, but still they'll have different properties, right? So this is not a good way of classification, right? So the first attempt, I would say not with respect to solid, liquid, and gases, but in terms of proper chemical properties, was done by Dobereiner, right? And we have something called as Dobereiner's triads, right? Okay, so what he did, triad means what? Triad means group of 3, right? So he grouped elements into group of three, elements like this, okay? And you have to understand that on all the periodic tables, in all the periodic classifications, all the attempts which are made, right, we have to understand what is the periodic function. What is the periodic function? What is the basis for classification? Based on what we are classifying, right? So here we are classifying based on atomic mass, right? Okay. Right. And we know what there's a difference between atomic mass and mass number, okay? There's a difference between atomic mass and mass number, but again, we'll be using them similarly, okay? But it is not exactly same, right? There's a subtle difference there, right? Okay, now what is the main thing here, right? If you take the average of first and third elements of atomic mass, we are going to get the second element's atomic mass. That's what is written here. Atomic mass of first element plus atomic mass of third element divided by 2, we are going to get the atomic mass of second element, right? And this was happening, okay? But he was able to get only 3 triads like this: lithium, sodium, potassium, chlorine, bromine, iodine, and this magnesium, calcium, and barium. Only this he was able to make. Other triads, whatever he made, was not falling into this category. What category? The average category, right? That was the problem, right? So what are the demerits, right? So it's written here, not all triads were following the law of triad. What is law of triad? This one, right? Atomic mass of first element plus atomic mass of third element divided by 2 is not giving us atomic mass of second element for all the triads, right? And second problem was isotopes, right? So we know they will have same atomic number but different mass number, right? Since we have different the periodic function here, it is based on atomic mass or mass number. All the isotopes should have different places, right? One hydrogen 1, hydrogen 2, hydrogen 3, all should have different places. But again, like that was not done, right? But that has to be done according to Dobriner, right? Again, all the isotopes, even though they have different mass numbers, they have similar chemical properties. Okay, but again, they were not able to be placed in the different things, different boxes. Right? That was a problem. And then the other problem would be there was no space. Right? There was no space for new element to be found out. Right? If at all a new element is found out in the Dobriner triad, the people were not able to place the new element found out. Right? Okay. Then we moved on to see this Newland's laws of octaves. Right? We have something called as Newland's table. Right? And here also the periodic function is going to be in terms of atomic mass. Right? And here we follow something called as law of octaves. What is law of octaves? It is whenever we arrange the elements in the ascending order of atomic mass, 1, 2, 3, 4, 5, 6, like that we arrange, right? Every 8th element will have similar properties, right? Every 8th element will have similar properties, right? And there was no scientific explanation for this. This guy, Newland, was actually a musician, right? So he said that we know that sa, re, ga, ma, pa, da, ni, sa, again, sa is repeating, right? Like that. He said, since the musical notes are repeating, he said the elements can also repeat their properties for every 8th element. Right. So again, what are the problems we face? We face isotopes is a problem because here also that the periodic function is going to be atomic mass, right? And then obviously no place for new elements. There was no place here for new elements to be found out, right? And then we moved on to see this, I would say, important periodic table, that is Mendeleev's periodic table, right? Now here also we say that the periodic function was taken to be atomic mass only, right? Now, the major advantage, one big advantage compared to the other two, is that he indeed gave new space. He gave spaces for new elements to be found out. If at all a new element is discovered, he gave place. He also predicted where it should come also, right? Where it should come, how it will behave, all these things were predicted by Mendeleev's, right? So what happened here, for example, he took boron. After boron, the place was empty. Okay, and he called that element as Eka boron. Eka means same. So what do you mean by Eka boron? Means there is going to be one element which is going to have similar properties to boron, right? And the next was also empty, right? And he called it as, after that, actually it was eventually found out. Eka boron was eventually found out to be aluminium, right? And again, the next place was empty. He called it as Eka aluminium, and that was found to be gallium, right? Same way for silicon, he called Eka silicon. That was called germanium. Right, so this was a very good thing he did, right? Even though there were some flaws, we will see what are the flaws, but this one, right, he was able to give new spaces for the new elements to be discovered and put it there, right? That was a very big advantage, right? Okay, then there were some problems. The problem where, with respect to this nickel and cobalt, right? Nickel was having 58.71, cobalt was having 58.93. So first, obviously, nickel should come, then cobalt should come. Right, but in this period, what he did, he first put cobalt, then he put nickel. Is it not right? Just for sake of chemical properties, if the elements in the same vertical columns are going to have similar chemical properties, he said, right? So first nickel should have come, then cobalt should have come. But what we see is cobalt is coming first, and then nickel. He didn't have any, explanation for this. Why is this happening? Right? Okay. So again, the problem was with isotopes because he was using atomic mass as the periodic function, right? And the ascending order is not exactly followed. For example, in the case of copper, cobalt, and nickel, right? Okay, so this is where we stop last class, right? So today, what are we going to see is your modern periodic table. Okay, we are going to see modern periodic table, right? Okay, now this is the first time. This was actually modern periodic table. If you ask me, who was the main contributor to this, there is no one perfect answer because different scientists gave different contributions to the particular periodic table. Okay, but I would say the work was started by someone called as Moseley. Okay, right? He was a scientist. Okay, he was the first one to at least give a draft of this part of the modern periodic table, and after that, so much advancement happened and stuff. But I would say the basic modern periodic table was given by the scientist called as Moseley. Okay, right. So here is the first time in modern periodic table is the first time they used atomic number as the periodic function. Right? This is the first time they used atomic number as the periodic function. Okay, in all the other cases you saw, right? What are we using? We are using atomic mass as the periodic function, right? So the main problem was isotopes was actually solved. Is it not? Because isotopes are going to have same mass, same atomic number, but different mass number, right? If I use atomic mass as the periodic function, then all the isotopes should have different places. But if at all I use atomic number, all the isotopes will have same atomic number only. Say hydrogen, whether it is 1 or 2 or 3 or 4 or whatever it is, all of them can be placed into a single box, single place, right? So that is the main problem which was solved. Not that so many problems were solved, obviously, right? Okay, fine. Now, right? So that was the first thing, right? The periodic function here, it is going to be atomic number. Okay, so the entire periodic table is actually divided into groups, which are the vertical columns, right? And we have something called as periods, right? Which are going to be called as, which are nothing but your horizontal rows. Horizontal rows. Okay, so basically the entire periodic table was looking like this, right? Entire periodic table was looking like this. Okay, this particular row, this particular vertical column was what is called as groups, right? And these horizontal rows are what are called as periods, right? So now how many periods, how many groups we have in periodic table? If someone asks you, you have to tell them that we have 18 groups. That is, we have 18 such vertical columns like this. 18 groups will come, right? And how many periods we have? We have 7 periods. Okay, we have 7 periods, is correct? Yeah, I think 7 periods should be correct. Okay, right. So people, right, what is so special about these groups and periods? Right now, it is very simple. Like what happened is here we are going to here, as I said, we are going to use the atomic number as the periodic function, isn't it? Right. So all we did was arrange the elements in the ascending order of atomic number. Right. Arrange them in the ascending order of atomic number. Right. Now they are done in such a way. Right. They are done. Ascending order of atomic number is not just randomly weighted. Okay, 1, 2, 3, 4, 5, 6, 7, 8. It's not like randomly weighted. Right. It was done in such a way. It was done in such a way that the elements in the same group, right? Elements in the same group, right, had same number of valence electrons. This was a very important thing, right? This is a very important thing. Okay, when the elements are arranged in the atomic mark in the ascending order of atomic number, but not randomly, how they arrange? They arrange in such a way that elements in the same group, right, will have same number of valence electrons. Okay, they'll have same number of valence electrons. For example, if I take group 1 elements, right, that is the first vertical column, right? If I take group 1 elements, what or not we had lithium, sodium, potassium, rubidium, and cesium. Okay, right? Now, what did it tell? It's not about having same number of electrons. It is about same number of valence electrons. We know what is valence electrons, right? Valence electrons, nothing but electrons in the valence shell, the last shell. Right? Same number of electrons in the valence shell. Right? If you check it, lithium is going to have atomic number 3, so it is going to have 2,1 configuration. Sodium is going to have atomic number of 11, so again it is going to have 2,8,1 configuration. Potassium is going to have 2,8,8,1 configuration. Rubidium would have had 2,8,18,1. So what are you seeing? All of them are having same number of valence electrons, 1 electron each in the group 1, right? So if you go to group 2, right, you will see, like, for example, if I take group 2, right, what is going to happen? Here we are going to have beryllium, magnesium, calcium, strontium, and barium, right? Beryllium, magnesium, calcium, strontium, and barium. Right? So if you check again, beryllium is going to have atomic number of 4, which is going to have 2,2 configuration. This is going to have 12. We are going to have 2,8,2 as the configuration. This is going to have 20. So we'll have 2,8,8,2 as the configuration. Again, what are you seeing? All the elements in the same group will have same number of valence electrons. Right? That is a very important point. Very, 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 very important point. Right? Fine. Let us look into the periodic table once. Let me download the periodic table for you and show you what exactly are there. Let us, this is, okay. Okay, I hope you're able to see it, right? Okay. Now, people, as I said, we are going to have 18 groups, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, totally we have 18 groups, and this is exactly how the periodic table looks. Okay, right. Now, if I check the periods, right? Say I told you the horizontal row is the periods. This is period 1, period 2, period 3, period 4, period 5, period 6, period 7. What is this? Okay, like we should not be considering these two as periods, okay? Right, these are different, right? We don't have to worry about it now. What are these? Okay, but totally we have 7 periods. That's all you have to understand. Okay, right. Fine. So we have 18 groups and 7 periods. Right. Now look at how it is arranged. Right. See, hydrogen is having atomic number of 1. Next comes helium, atomic number 2. Then what we did? We went on to see the third element, that is atomic number 3, atomic number 4, again atomic number 5, 6, 7, 8, 9, 10. Right. Then again coming back to 11, 12, 13, 11, 12, 13, 14, 15, 16, 17, 18. Again coming back 19, 20, 22, like this, it keeps on going. Okay, right. So what you have to understand is period 1, right? Period 1 has only 2 elements. That is, your first horizontal row has only 2. One is hydrogen, the other one is helium. Okay, right. Period 2 and period 3, right? Period 2 and period 3 has 8 elements in it. Okay, you can see 1, 2, 3, 4, 5, 6, 7, 8. All these things are there. Right. Now, period 3, not period 3, period 4 to period 7, all of them will have 18 elements in the periodic, in the same period. Okay, this is again very important point. Period 1 has only 2 elements. Okay. Period 2 and period 3 has 8 elements in there, right? And all the other periods, period 4, period 5, period 6 to period 7, all of them will have 18 elements in their periods. Okay. Now, why is it like this? Why is it that different periods have different number of elements? Is because I want to satisfy this. What I have to satisfy? Every element in the same group will have same number of valence electrons. That's very important. Okay, same number of valence electrons. Right. According to that, it was designed. Right. It was designed in such a way that this many elements only should come in the group, such that the elements in the same group will have same number of valence electrons. Okay, right, fine. So all of any group you check, all the elements in the same group will have same number of valence electrons. Okay, say for example, let me check group 13. Right, let me check group 13 for example. We have what? We have boron, aluminium, gallium, indium, thallium. Right. Okay. Now, okay, I'll come back to this later. This is different. Okay, this is not an element. Right? This is an element which is yet to be discovered. Okay, this is an element which is yet to be discovered. We'll speak about this later. I'll tell you how you should find out. Okay, right. So people, boron is having an atomic number of 5. Right. So what will be the configuration? 2, 3. Right. Aluminium is going to have an atomic number of 13. That will have 2, 8, 3. Gallium will have 2, 8, 8, 3. That is 16, 19, 21. Right. So like this, if you check, every element will have again same number of valence electrons. Okay. Same number of valence electrons. That's a very important point. Right. Now, if they have same number of valence electrons, why? I mean, what is so special about it? Right? Okay, fine. We understood that there are going to be this many elements in the same in the periods. That is, period 1 has 2 elements, period 2 and 3 has 8 elements, period 4 to 7 has 18 elements, and we also understood that this was done in accordance to this particular thing. Every element in the same group will have same number of valence electrons. Okay, but what is so special about having same number of valence electrons? People, we know that it is because of this number of valence electrons only how their chemical reactivity will be dependent. Is it not? Right? For example, if I have, say, sodium reacting with oxygen, it is going to form Na2O. Say, same way with potassium, if it reacts with the oxygen, it is going to form K2O. Right? This is in group 1 elements, for example. Say, when I go to group 2, magnesium reacts with oxygen to form MgO. Right? Calcium reacts with oxygen to form calcium oxide. Right? Okay, so we have to be very, very careful with this. Now look at this, right? Now you have Na2O, K2O, so it is of the form M2O. Same way, here you see that it is forming MgO, CaO, so this is of the form what? This is of the form MO, right? So you see every element in the same group, because they have same number of valence electrons, will have similar chemical properties. Right? How they react with another element, say for oxygen, say for example, in the case of chlorine, bromine, all these stuff, right? How they react with another element is going to be exactly same. Why? Because they form same kind of cation or anion. Is it not? Now, it is very interesting, right? All of these elements, can I say, will form M plus cation because all of them are having one valence electron in the valence shell. Right? And for me to satisfy octet or duplet, what I should do? I should be removing 1 electron, right? If I remove 1 electron, all of them become stable because they're going to have 8 or 18 or 1 and 2 electrons in the valence shell. So all of them will form M plus cation. That is monovalent cations. Right? Same way in group 2, what we are seeing? We are seeing that all of them are having two valence electrons. So all of these will form M2 plus cations. Okay, all of them will form M2 plus cations. Okay, right? Fine. So that is a very important thing. Since they have same number of valence electrons, they form same kind of ion, right? And so they have similar chemical properties, right? That is the most important part. Okay, right. Now the question can be coming like this. Okay, see, we have to know this group, right? Not all the elements in this group, but at least the first 3 elements in all the group: lithium, sodium, potassium. See, hydrogen should not be here. Hydrogen should be somewhere here. Okay. See, it is given in some other color. It is not belonging to group 1. Same way, hydrogen also does not belong to this one. It is somewhere here. Okay, right? Anyways, okay. So we have to understand at least 3 elements in every group, right? Because questions can come from that. All right. Okay. So we have to know lithium, sodium, potassium, beryllium, magnesium, calcium. Okay, and you don't have to worry about this for now. You don't have to worry about this for now. Okay, right? And then if you go here again from group 1, we need to know what I'll tell you. Wait, group 1 we need to know, group 2 we need to know, right? And in between that is group 3 to group 12, right? This you don't have to worry now. Okay, group 3 to group 12, you do not have to worry, right? But we have to know group 13 to group 18. That we have to know, right? Only these groups for now we have to remember. Now again, not the entire element, but at least three elements in every group we have to know. Okay, so here you have to remember magnesium, boron, aluminium, gallium, carbon, silicon, germanium. Okay, nitrogen, phosphorus, arsenic, oxygen, sulfur, selenium, fluorine, chlorine, bromine. Iodine also you can remember, that is very easy. Okay, neon, argon, krypton. Like this in every group, that is group 1, group 2. Okay, then group 13 to 18, right? We have to know what are the first 3 elements in every group. If you don't remember, the solving questions will be very difficult. Okay, solving questions will be very difficult. Okay, right? They'll ask question like this, right? They'll ask question like this. There is an element, right? There is an element which belongs to group 2. Okay, say that is M, right? And there is an element, right, which belongs to group 17, right? And that is some X, right? Now, if they react together, what is the formula of the group? They'll ask like this. Okay, there is one element M which belongs to group 2, right? And there is another element which belongs to group 17, right? And that is called as X. And if they react together, what is the formula of the compound? They'll ask, right? Now we have to know for all the elements, what is their valency? What is their number of valence electrons? Okay. Now remember, people, remember in this group 1, right? I'm talking about group and the number of valence electrons. Okay. So now group 1 will have 1 valence electrons. Group 2 will have 2 valence electrons. Okay. Now directly we can go to group 12, right? Group 12, not group 12, group 13. Right? When I go to group 13, they will have 3 valence electrons. Okay. And when I go to group 14, they're going to have 4 valence electrons. Group 15, 5 valence electrons. Group 16, 6 valence electrons. Group 17, 7 valence electrons. Group 18, 8 valence electrons. This we have to know. Okay. Group 1, it's very easy to understand, right? Only for group 1 and 2, directly it will come. Right? From group 13 to 18, it is very easy to understand. It is number of valence electron is what is that? 10, or say group number minus 10. Is it not? A group number is 13. Like group number is 13 minus 10. If I do, what I'm going to get? I'm going to get 3. Same way for 14, 4, for 15, 5, for 16, 6, for 17, 7, for 18, 8. Okay. Right? So this we have to remember again and again. I'm telling it's very important, right? So we have to remember for these groups, group 1, group 2, then group 13 to 18, we have to remember how many valence electrons the elements will have in that group, right? Once you know this, right? Once you know this, it is very easy to answer these kind of questions. It is very easy to answer these kind of questions, right? Now let us check how to answer this question now. Now they're telling that some element in group 2, right? So can I tell it is going to have 2 valence electrons? So some configuration, and at the end it is going to have 2 valence electrons. Okay, right? So can I tell this one is going to lose 2 electrons? It will lose 2 electrons to satisfy its octet to form M2 plus. Is it not? Right? It is going to lose the 2 valence electrons it has, right? To form what? To form M2 plus. Okay, right? Then what? Okay, that is okay. Fine. Now what is going to happen in group 17? I know group 17 will have 7 valence electrons. Is it not? Right? So what has to happen? Can you tell me what kind of ion it is going to form now? Quickly. This element X, right, will form what ion? Tell me. We understood that it is going to have 7 valence electrons, right? So we know for satisfying octet what has to be done. And after satisfying octet, it is going to form an ion. What is that ion form?
Sir, it will gain 1 electron, sir.
Good. Okay. If it gains electron, what will happen to the charge?
And minus, sir.
Okay. So can you tell me what is the exact ion name we wrote here? M2 plus, right? Like that, how will you write it?
X minus.
That's it. Very good. Right. So we understand that it is having 7 valence electrons. Obviously, this X has to accept 1 electron to form X minus. Right. Now, once you know what is the charge, now we know how to make the formula. Swap the charges, right? M2 plus, we have X1 minus. So we swap like this. So we are going to get MX2 as the answer to this question. Very simple, right, people? Right? So the moment you know the number of valence electrons, you know whether you have to lose the electron, whether you have to accept the electron, how many electrons accepted, how many electrons lost. Like that, will be able to form the ion. The moment you form the ion, you'll be able to swap the charges to get the atomic, to get the formula of the compound. Very, 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 very simple. Okay, right? These kind of questions, definitely question will come in your board exams. Definitely, short questions like this will come. Okay, right? So all that you have to understand is in each and every group, how many valence electrons are there for all the elements in the same group. That if you know, these questions can be a cakewalk. Very simple questions. All right. Okay. So let us do another question, maybe like this. Fine. They can also ask some. Okay, fine, no issues. Fine. So if I have element in group 1, okay, I have some element M in group 1, and I have some element in group 15. Right, I have some element in group 15, some that is X. Right, tell me what is the formula of the compound. If they react together, okay, what will be the formula of that particular compound?
Sir, will it be M3X, sir?
M3X is correct. Right, very good. So it's very easy to understand. Now this M will have 1 valence electron, right? And this X we told group 15 means it will have 5 valence electrons, right? So what has to happen? So both of them have to satisfy octet or duplet or whatever it is, right? So this M will lose the electron, will lose 1 electron to form what? To form M plus. Right, and this X is there, it is having 5 valence electrons. You should not say, okay, it is going to lose 5 electrons. No, what it has to do, it has to accept 3 electrons. Exactly, right? It has to accept 3 electrons to form 8 electrons in its valence shell. 5 plus 3 will become 8, right? So it is going to become X3 minus. Now that is very simple now. M plus, and we have X3 minus. This will come here, this will come here. So we'll form M3X. Absolutely correct. Okay, right? Fine. This is how question can be asked. All that we have to understand is how do you form octet, whether by losing electron or by accepting electron, And obviously for that, we have to know each and every element will have how many valence electrons. Each and every group will have how many valence electrons. That is the only thing which you have to remember. Okay. And second thing is there are certain group names which you have to understand. These are families, right? One group is one family because they're going to have similar properties. Okay. So this group 1 elements, that is your lithium, sodium, potassium and all, they are going to be called as what? They are going to be called as alkali metals. Okay. Group 1 elements are going to be called as group alkali metals. Group 2 elements are going to be called as alkali earth metals. Okay, and something called as group 70. Group 70 is nothing but your this thing, chlorine, bromine, fluorine, iodine, right? This group 70 here. Okay, now that one is going to be called as halogens, right? And you even have group 16, that is your oxygen family. Oxygen is here, right? Group 16, the first element is oxygen, right? That is going to be called as chalcogens, right? So these are different names of the families you can remember: alkali metals, alkali earth metals, halogens, chalcogens, right? So these are different commonly used names which you can remember also. Okay. Now another thing is left hand side of the periodic table. Left side of the periodic table are metals, right? Left hand side of the periodic table are metals, and the right hand side of the periodic table, are generally going to be non-metals, right? You can easily understand here, right? If you look into the periodic table, you see, right, lithium, sodium, potassium, magnesium, calcium, all these are metals, right? But here if you check carbon, nitrogen, oxygen, fluorine, everything here will generally be non-metals. Okay, right? That is also another story. Now you don't have to worry about this one for now, right? It's not like they're going to be neither metals nor non-metals. No, it is not going to be like that. Okay, right? So that is one thing you have to remember. The left hand side of the periodic table, we have metals, right? And the right, not generally, I'm telling you, generally, right? But right now the periodic table, you can have non-metals. But again, there can be some examples like this. For example, aluminium is a metal, right? But like same way, boron, fine, we can call it as a metal, right? Okay, but anyways, generally speaking, right hand side non-metals, left hand side metals will be there. Okay, that is another important thing which you can remember. Okay, now next thing is, right? Next thing is, right? How, like there's something called as atomic trends, right? There's something called as atomic trends. Basically, we are going to take one particular property, right? We are going to take one particular property, right? And we are going to see how that varies down the group and how that varies along the period. Okay, and we have so many atomic trends, but for your 10th class, we have only one, that is atomic size, right? That we have something called as atomic size. Okay, right? We are going to understand when I go down the group whether the size increases or decreases. Okay, when I go along the period from left to right of the period, maybe it is from your left to right, whatever it is, right? From left to right of the period. Now, if I travel to the periodic table, whether the size will increase or decrease. Okay, that also you have to understand. Okay, right. Now let us take any one group. Let us take first the group and try to understand what exactly is happening. Right. So people say, let us take group 1 only, and whatever you're going to see for group 1, that is going to be the same for any other group. Okay, right. So if I take group 1, say I have lithium, sodium, potassium, rubidium, cesium, whatever, right? So we know how the configuration looks. So we have 2,1, we have 2,8,1. Here we have 2,8,8,1, and here we have whatever, and it is going to have so many electrons and then 1. Right. Now, what are you seeing? You are seeing that when I go down the group, right? When I go down the group, the number of shells, right? The number of shells increases. Is it not? Say if you check for lithium, it is having 1, 2. That's it. Right. Now, when I go to sodium, it is having nucleus 1, 2, 3. Right. Now, when I go to potassium, it is having nucleus 1, 2, 3, 4. 4 shells are there, right? So what is happening? Since the number of shells are increasing, the size also increases, right? Since the number of shells increases, the size also increases, and that is going to be common for any group, right? This is not equal to infinite. I'm going to take group 2 instead of 1 electron. All that we are going to have is a different number of electrons, that is 2, right? So in general, people, in general, we can say that when I go down the group, the atomic size keeps on increasing. So sodium will have a greater size than lithium. Potassium will have a greater size than sodium. Like that, we can tell. Say, for example, I can also tell, say, for example, if at all I have fluorine, chlorine, bromine, iodine, right? Now, if I ask you, what is the, arrange them in the order of atomic sizes, right? Now, we understand that down the group, the atomic size increases. So iodine will have a greater size than bromine, than chlorine, than fluorine. So for the same reason, when I go down the group, the number of shells keep on getting added, right? So obviously what is going to happen? Obviously the atomic size keeps on increasing. Okay, right. That is one thing. Now, when I talk about the period, right? When I talk about the period, what is going to happen? Let us take period 2. Right? Why I'm not taking period 1? Because period 1 has only 2 elements, hydrogen, helium. We will not be able to study much about it. Right? Period 2 has so many elements, right? We have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. These are all the elements that are there in group in period 2. Right? Okay. Now let us write the configuration for this 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, and 2, 8. Okay, these are all the different configurations of all the elements in the period 2. Right? Now, people, what are we trying to do here? The number of shells are same only. All of them are having only 2 shells. Okay, fine. Then what is happening? In the same last shell, that is this shell, here I have 1 electron. In the last shell, we have 2, 3, 4, 5, 6, 7, 8. Right? In the same shell, we are going to keep on adding electrons. Right? Because of that, what is going to happen? Let us try to understand. Right? So, right, it's like this, right? Fine. Say I have the nucleus. Okay, I have the nucleus, right? And say the first shell, second shell. Right? Now, nucleus I know is hugely positive charge. Right? Nucleus is very strong positive charge, and it is going to have a very strong attraction for the electrons. Is it not? It is going to have a very strong attraction for the electrons. Is it not? So now, in case of lithium, we have only 1 electron here in the valence shell, right? It is going to have some attractive force. Okay, right. Now, in case of beryllium, what is happening? Beryllium is having 1 electron here, another electron here, and this nucleus is going to have attractive force for both these electrons. Right? Now, can I say the attractive forces? The attractive force is stronger here, right? Why? Because in case of lithium, we had only 1 electron getting attracted by the nucleus, right? But in case of beryllium, we have 2 electrons getting attracted by the nucleus, right? So obviously, the amount of charge if you increase, the amount of negative charge you increase, the nucleus is going to be very happy, right? The nucleus is going to be very happy. It is going to attract all the electrons you're going to give. So happy, I have so many electrons to attract, right? So because of this, what is going to happen? More attractive force is there. The valence shell is here, the nucleus is the center. If I have very strong attractive force, it is going to pull the electron towards itself. So not, it is going to pull the electron towards itself. More and more is the number of electrons. Stronger will be the attractive force. More and more will be the pulling power of the nucleus. Is it not? Right? So if it is going to very strongly pull the electron towards itself, what is going to happen to the size? Size will decrease. Is it not? Right? So you can understand, like maybe in this example also actually I've shown you, this is little big, this is little small. Why? Because I have 1 electron here, but here I have 2 electrons which are getting attracted. Right? Same way if I go for beryllium, it is having 3 electrons in the valence shell. Still more attractive force. If I go to 8 electrons, imagine the amount of force of attraction I can have. right? Very strong force of attraction, very strong pulling power. So the atomic size will be very small, very small, right? I hope you get the point, right? So what we can say is that in the group, lithium is going to have maximum size. This is how the size is going to vary, and neon is going to have the least size. Why? Because the neon has 8 valence electrons, and all of them are going to be very strongly attracted by the nucleus, right? Thereby the size decreases. If anybody has any question, someone else ask me anything. Okay, right? So what we can conclude is that when I go from left to right of the period, right? When we go from left to right of the period, the atomic size decreases, right? Atomic size decreases. So when I go down the group, number of shells keeps on increasing, so the atomic size increases, right? Now what happens? Since the number of electrons are increasing, the nuclear force of attraction increases, so thereby we can say that the atomic size decreases. Okay, right? I hope that makes a lot of sense to you, right? So yeah, that is about your atomic size. How is it varying down the group? It increases, and along the period it decreases. Okay, right? Fine. Now let us talk about this. What is the time? Okay, we have time. Right. So if we go to the periodic table, you will see some strange symbols like this: U U T U U P U N O. Anything else is there? Right. So like that, you will have some weird symbols like this. Okay. Now, what are these things? These are, whenever we write U something, whatever this is, these are elements. These are elements which are still to be discovered. Still to be discovered. Okay. They did not find these elements yet. Okay. They are still to be discovered. Okay. So that is what you have to understand. Okay, UUT, UUO, whatever, right? Whenever you see this U generally, not only you can have uranium also. Don't be hasty about this, right? But UU, like that, if you check, right? UN, something like that, if you check, that those are elements that are actually going to be still discovered. They are not yet discovered. Okay, right? That is another thing, right? And next thing is, actually, it is not there in your syllabus, but you will be able to name them also very easily. Like very simple. I can tell you how it names. So for example, if I have say 1 1 0, something like this. This is the atomic number. And this is the atomic number of the element, right? And say it is not found out yet. It is not discovered yet, right? So what can I write is, remember, for 1 we give right? And for 2 we give bi. Right, for 3 we give try. Like this we give the symbols. Okay, right? So here we have 1 1 0, right? And for 0 we give nil. Okay, and after the third this thing, right? After the third, whatever the number is, you have to finish with IUM. Okay, you have to finish with what? IUM. Okay, now here we have 1, so we write okay, and second number is also 1, so again we have and we have 0, so it is going to be nil. Oh God, what is wrong? Oh God, there is something wrong. Okay, so I told you. Okay, so here something is wrong. 1 second, guys. Right, so okay, done. So we have 1, so we write because it is UN for 1, And same way for another one is there. So un, and for 0, we write nil, and that's it. What you have to end after this? IUM. So if I write this properly, the name of this element is nilium. Right? Say, for example, if I write 1, 1, 2, or say I'll write 1, 2, 2, something like this. Right? If I have an element which is having atomic number of 1, 2, 2, how do we name this? For 1, it is un. For this thing, it is bi. Right? I think it's, yeah, bi. Right? Again, for this thing, it is bi. Again, we'll write LIUM. That's it. Again, 2 is there. So bi. Again, we'll end with LIUM. Very simple. Right? So whenever you see this kind of UN, B, UNT, something, 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 that means these elements are not yet discovered. Okay, right, fine. So these are all the amazing advantages of having the modern periodic table, but still it has its own problems, demerits. Okay, now though I would say only one demerit is there for now. That is the place for hydrogens. Right, the place for hydrogen is very controversial. Right, why is it controversial? Look into this. Say hydrogen is having an atomic number of 1. Right, so it, now you look at this, it can remove 1 electron. I can remove 1 electron from hydrogen to form H plus, right? Or this H can accept 1 electron to form H minus. This is your hydride. Right, now is this not similar to group 1? Because group 1 elements can form M plus ions, right? But if I check this one, H minus it is forming, this can be formed by group 17 elements, because they will have 7 valence electrons to accept 1 electron to form 8. So they can form like this X minus. So that H minus is also following that. Is it not? Right? So the problem is it can either be placed in group 1 or it can be placed in group 17. That is why it has some random place. It is not part of any group. Okay, it is not part of any group. That's why IPAC said, okay, you keep it somewhere in between. Okay, so that is a very big problem in case of modern periodic table. Okay, where to place hydrogen, whether in group 1 or in group 17, because it has both the properties. Okay, where to place it is a big problem. And I would say that is, there are a few other problems also, but for 11th class, this much is enough for you. Okay, right, with this, the chapter is completed. Right, the chapter is done. Okay, and successfully, we have completed your portions for 10th. Okay, so maybe from next class, we'll be having only revision. Any questions anybody has? Do you want to ask me any questions? Okay, if that's the case, we can wind up the class. Thank you so much, people. We'll end the class.
Thank you, sir.
Thank you, sir.